So right up here we have a line, a point F not on the line, a point D that always lies on the line as shown here, and we're also going to throw in the perpendicular bisector of segment FD. In simple English, think of the perpendicular bisector as the crease that I would form, the fold or the crease, if I were to fold D onto F on paper. No matter where D lies, that would be the crease if I folded D onto F. So what I want to know is, what do all possible creases look like? Let's actually turn the trace on and find out. Look at this. This is crazy. All possible fold lines folding D to F result in a figure that looks like this. I've done this on wax paper and it looks the same. And would you look at that? What do you see? If you said parabola, you're absolutely correct. That curve right there is a parabola. But why? Why do we get a parabola? Let's look at it and find out and see. Let's turn the trace off first and check it out for ourselves, right? Let's actually take point D and we'll draw perpendicular up until it hits the perpendicular bisector right there, or the fold line, right? If a point lies on the fold line, the perpendicular bisector, it's got to be equidistant from the endpoints of that invisible segment FD there. And that's what makes a parabola a parabola. So if I turn this trace on and move D, look at that. A parabola is a set of all points in the plane so that the distance from any point on the parabola to a fixed point called the focus and the fixed line called the directrix are always equal.